Hello everyone, this is Göksu Avdan from Missouri Western State University, and then I am going to be the one who is presenting my student's work, who is the Colby Scott Schwager. And let's start with the title since we have a limited time, like 10 minutes to present everything. This study is named as Bio-Based Neck Orthosis Design, Structural Comparison of Circular, Elliptical, and Honeycomb Patterns using Finite Element Analysis. So, in the background and motivation, the cervical orthosis stabilize the neck after injury or surgery and support the patients through rehabilitations. Because these are worn devices, comfort and breathability matter as much as the strength. Additive manufacturing, which is the 3D printing, lets us tailor shape and ventilation while reducing the weight. At the same time, there is a push for sustainable materials that don't compromise safety. Our work asks how internal ventilation patterns and material choice together affect the mechanical behavior in this sustainability goal we are going to cover in today's presentation. We focus on two different questions when we start on this research. The first one was how do common ventilated patterns such as circular, elliptical, and honeycomb influence the stiffness and stress? Second question was, can a bio-based material, hemp bioplastic, this was the choice we have for our sustainable material by checking the current literature review, and then see if this material is performing the same or similar to conventional polyamide, which is PA12. Our contributions are a direct side-by-side comparison of patterns and materials using finite element analysis and a digital first workflow that helps teams make early design decisions before printing prototypes. We modeled the cervical orthosis in Autodesk Fusion 360 and fixed the wall thickness at 4 millimeters for a fair comparison. The three internal patterns were selected for their practicality, the circular for simplicity and uniformity, elliptical to improve the airflow and reduce the weight, and the last one, which is the most promising one, the honeycomb one, is to combine ventilation with efficient load transfer. All designs target the same external fit while changing the internal architecture. What I can say is that we use Autodesk Fusion 360, which is the available software in our school. Other researchers can use different kind of softwares to reach the similar results in this analysis. So in this slide, we also compare the materials we have used. The first one was the PA12, and then the second one is the bio-based alternative, which is hemp bioplastic or HBP. So if I say HBP, you can refer to hemp bioplastic. The typical property values used in simulation were for PA12, a young modulus around 1700 megapascal. Poisson's ratio was 0.39. The density of this material is 1.01 grams per cubic centimeter, and a yield strength was around 45 to 50 megapascal. On the other hand, for the hemp bioplastic, which is HBP, our young modulus was equal to 4420 megapascal. Our Poisson ratio was 0.32. Density is 1.20 gram per cubic centimeter, and our yield strength is near to 50 megapascal. Both are feasible for additive manufacturing, which is 3D printing, but HBP emphasized our sustainability goal in today's presentation. So let's start with the finite element analysis setup after we are done with our design. We used a solid tetrahedral mesh with a global element size near 5 millimeters and local refinement to 2 to 4 millimeters in curved or thin regions and expected high stress zones. Loads were applied at the upper inner surface to reflect key neck movements, which is 287 newtons for extension, 165 newtons for flexion, and 208 newtons for lateral bending. Our primary outputs were total displacement, which indicates overall stiffness, and von Mises stress, which we compare our to material yield. In terms of results, by using this 3 different pattern and 2 different materials in our research, which we can tell across all loads and both materials, the honeycomb pattern delivered the lowest displacement, meaning the stiffest response. With PA12 in honeycomb, extension displacement was roughly 0.657 millimeters. With HBP, it was about 1.405 millimeters, an increase of about 114%. Similar ratios held for flexion and lateral bending. This tells us geometry strongly controls global stiffness, and honeycomb is consistently efficient choice comparing to what we have in circular and other design options. Overall, lower bars means stiffer response. Honeycomb is consistently the lowest one we have in here. For stress, the differences between materials were very small. Values stayed well below yield for both PA12 and HBP. Honeycomb again tended to produce the lowest stresses. For example, under extension, PA12 honeycomb was around 8.6 megapascal, and HBP honeycomb around 8.8 megapascal, only a few percent apart. So while HBP displaced more, peak stresses remain comparable and safely under material limits. Overall, the stress remained well below yield for PA12 and HBP, with honeycomb typically lowest or near lowest one in our design preferences. So as an interpretation for this study, why does HBP displace more despite a higher modulus? We suspect an interaction effects between geometry and constitutive behavior, along with the lower Poisson's ratio and higher density influencing the response. The main point is that architectural patterning can outweigh nominal property differences. Honeycomb distributes loads efficiently, improving stiffness and keeping the stress low. How about the limitations and the next steps for our research, and then the key takeaways from what we have today? We did not model soft interface padding and evaluate comfort and thermal behavior on our users. Those are very critical next steps for the prototypes. We also plan to incorporate AI-driven optimization for patient-specific designs and test hybrid patterns. Overall takeaways from our today's presentation: honeycomb is a strong default for ventilated neck orthosis. HBP appears structurally safe and offers a sustainable path, and digital FEA, which is finite element analysis, is a cost-effective way to down select designs before printing and then the trials. So that's all we have for today's presentation. Thank you all for watching.